So I guess the first question is, what do I mean by a moment entropy inequality? So for the most part, what I want to talk about today is a very straightforward question. And what I want to do is take this very simple question and just beat it as hard as it can possibly be done. Okay, so for the most part, we're talking about one-dimensional integrals. We're talking about one-dimensional integrals where there is no cancellation. We're integrating a non-negative quantity in particular. So we have, for example, a function f. We will assume that it's smooth, defined on some interval, probably the whole real line, but not necessarily. And we have some probability measure on the real line. And what we want to do is estimate the absolute value. We take the modulus of f and integrate it with respect to this measure mu, and the result we want to estimate from below. Okay, since it is a non-negative quantity, there's reason to expect that you could estimate it from below. There are two trivial estimates that I want to sort of put up at the very beginning. The first here is to say that, well, if you estimate the integral of this absolute value of f here, it's certainly bigger than or equal to the inf of the modulus over the whole interval in which everything is defined. Okay, and and there's no constant here because this is a probability measure. Okay, so this statement is just saying, well, just take the point where the function is smallest. Everywhere else is bigger than that, and so the total integral of this non-negative function is just bounded below by the place where it attains its minimum. This is one trivial inequality. Another sort of trivial inequality is the following. It's trivial in the sense that it's a one line to prove. It's not trivial in the sense that it's not so straightforward to write down. But the idea is the following: that you take you now consider sets E that are contained in the interval, and these sets are closed sets, for example. On any particular set E, you're allowed to take a sup instead of an inf, so it's significantly better in that regard. But the bad news is that at the end of the day, you're not really allowed to take any set that you want, but you have to take the worst one in this way. In other words, what we're doing here, for example, is we're looking at the measure mu. We're going to take a set E of mu measure 1 minus epsilon, on which the modulus of f is smallest. Okay, so we throw away a set which has almost all of the mass, and it's the set where the modulus is smallest. But then on the bright side is that since it's smallest, that means on the remaining epsilon of the mass, it's bigger than that number. Okay, so we get this trade-off that you get to replace this inf here with a sup, but there's still an inf here, which is sort of unfortunate. And so these are the two trivial estimates, and I want to say that neither one of these is very good in a way that will be precise later, but especially from the point of making meaningful applications. But first, I just want to say, that actually neither of these two estimates we should think of as being very uniform. And what do I mean by uniform? Well, I mean we have we're interested in not just studying a particular function f, but certain classes of functions f, like polynomials of degree d or something like this. The reason that I want to claim that this estimate is not uniform is because, well, in particular, as f varies, the particular point that you have to look at to find the inf changes. Okay, so the right-hand side, even though it looks like a nice simple estimate, this inf itself, the particular point that we're looking at, depends on what your f function is. Okay, so you don't have total freedom. You're restricted to look at a particular point or a particular set, and what that point is or what that set is depends on the function that you're integrating. Okay. So why are these called moment entropy inequalities? Well, the moment entropy inequality is a statement from information theory, which says that if you take a probability density function g, and you compute its second moment here, that this integral is never too small, and in particular it's bounded below by some constant times the exponential of twice the Shannon entropy of g. So the Shannon entropy, remember, is minus the integral of g times log of g. Okay, so we have some quantity here this g would place the role of a measure here, and this t squared would play the role of our particular function that we've chosen. Okay? So what we've got is it says that this integral can never be too small in terms of a number that depends on the measure. Okay? So in particular, in information theory, this is important because there you can compute what the minimizer is, and it turns out that the minimizer is Gaussian. Okay. For my purposes, we won't be really concerned so much in finding exact extremals or sharp constants. This sharp constant is known. But the question is, how can we prove inequalities of the same flavor for general families of functions, where not necessarily just a t squared, but where this t squared is allowed to be replaced with some more general non-negative function. Okay. Morally, this problem is the same in the sort of context of harmonic analysis. It's very much related to the question of studying the size of sub-level sets of smooth functions. Okay, because I mean, one of the most natural things that you can do is take this t squared, throw away sort of neglect the contribution of this integral where t squared is small, and then estimate this integral from below just using information about when t squared is large. And so you need to know information about the sublevel sets of t squared. And for more general functions, one approach would be the same idea, to look at the sublevel sets. In particular, there's a considerable amount of work done on sublevel set inequalities, in particular in one dimension, which is for the most part what we'll be talking about today. In particular, there are sharp constants known, given that the function f, for example, has a kth derivative which is non-vanishing or something like this. And they're much more sophisticated related problems in which people study sublevel sets by taking the characteristic function of a particular sublevel set of a function and turning it into a kernel of an operator, and then asking questions about the operator norm of this operator. Okay, so these are all very much related. But what I want to talk about is much simpler. Okay, so just as an example, I want to sort of point out that if you take this probability density G to be uniform on some Lebesgue measurable set, we can compute the Shannon entropy, and there should be a log here, by the way. This should be the Shannon entropy of this probability density is log of the total measure of E, and so the inequality from before tells us that, well, if you integrate t squared on any Lebesgue measurable set, the very smallest that this can possibly be is some constant times the third power of the measure. Okay? So in other words, we have this nice uniform statement that says that as long as your set is not small, then the integral is guaranteed not to be small. Which makes sense, right? Because this function only vanishes at one point, and if you have a large set, then you're guaranteed that some proportion of that set is not going to lie too near to that one point. Okay, and that's basically the one-sentence statement of how you would prove an inequality like this. Okay. The desirable features from the point of applications are that this inequality is translation invariant, so you can translate the set E, and it doesn't affect anything. The constant C is of course independent of E, and the lower bound of a desirable feature is that the lower bound is always not trivial unless you have a null set anyway. Okay. The downside is that it's not clear necessarily how you would generalize an inequality like this to take out the particular t squared and replace it with something more useful. So the reason to study such things, I suppose that there are a number of reasons. The reason that I was initially led to questions of this type comes from the problem of proving LP-LQ estimates for one-dimensional averaging operators. So there was a paper in 1998 by Christ that established a very combinatorial approach to proving these sorts of inequalities. The idea in his paper is that you look at more or less a composition of your operator t. So in his paper he studied convolution with measure on the curve. The curve is defined by t squared, t cubed up to t to the d in Rd. Okay, so you take this particular curve, you restrict it to t between -1 and 1, you get a measure, and you convolve functions with this measure. The idea being that since it's an averaging operator, it should somehow smooth out the function, and there are a variety of different ways to measure the smoothing. one way would be to look at the improvement of the integrability exponents. And what it boils down to is you look at repeated iterations, compositions of this map, and I mean, I'm leaving out a lot of steps, but I want to sort of zoom in on one particular feature of the proof, and that is it's reduced to integrating the absolute value of a van der Waals determinant over a set, sort of a set in RD, that you know very little about, except that you know its width in each of the coordinate directions. You know it's not too short in any one specific direction. Okay? And you now take this set and you want to integrate the absolute value of this van der Waals determinant. And what you can do, what was done originally, is to just more or less play a game like I already mentioned. You just sort of direction by direction, you cut out little intervals where the van der Waals determinant is small, and you make an estimate from below by just cutting things out. The proof of the general case, so modulo boundary estimates, as due to tau and Wright. In this case, it's not necessarily convolution, it's not necessarily the specific curve, but they have a general prescription for given a particular family of curves, and you average functions on this family of curves. They have a sort of whole combinatorial structure that tells you exactly which LPs get matched to which LQs based on some geometry of this collection of curves. Okay, and the point that I want to make is that certainly the work of Tau and Wright is very much based on the original idea of Christ. There's a lot of new machinery tacked on, but the point that I want to make is that that really the only new piece of machinery that really changes the story is that Tau and Wright have a more sophisticated way of estimating one-dimensional integrals than just cutting out intervals. Okay. So the way that Tau and Wright formulated the problem is the following. So instead of thinking of the operator directly, they think of a bilinear form. So the idea being that by duality, if you look at this bilinear form and it's bounded on some product of LP spaces, then it would define a nice operator, and that operator is an averaging operator over some curves. So the geometric way that you look at it is you take two functions, f and g, which live on, say, Rd. We have two projections, pi x and pi y. And these projections are, first of all, the differentials are surjective, and they have one-dimensional kernels. Okay, so if you straighten all of this out and you use Fubini's theorem and things like that, you'll see that this is the sort of bilinear geometric way to describe what you're doing when you're averaging a function over a family of curves. Okay, so for convenience, we'll assume that these vector fields x and y are the vector fields that are annihilated by these differentials. We'll assume that if you take sufficient number of Lie brackets of x and y with each other, that eventually everything vanishes. Okay, this is the correct geometric interpretation of these vector fields sort of being associated to polynomials. Okay, so we'll assume that there's some structure here, and that these vector fields are allowed to interact in some complicated way, but at some point it just dies and everything is identically zero. Okay. And so the paper of Tau and Wright says that, well, so you take these two vector fields, you form various commutators, and you look for collections of commutators that span, and then based on how many x's versus how many y's you took, there's an elaborate combinatorial formula that says, well, count how many times you use an x and count how many times you use a y, and then plug these into some formula, and it specifies an LP LQ pair that this bilinear form is bounded on. And it's also sharp in the sense that, well, they fail to get any estimates of any kind on the boundary, but they show that, well, up to epsilon, all of their results are sharp. That you can't do better than epsilon, more than what they had already showed. Okay. And the thing that makes this situation so complicated is that we've now got a function that we need to integrate from below. And this might be a little bit cryptic now, but hopefully in the next slide it'll be a little bit more, make a little bit more sense. The idea is that we have some function that we need to integrate, and there's a specific point that we want to, so we want to integrate this one-dimensional function from below using information about the function at one specific point, which is pre-specified. Okay? So let's see. So here's a little bit more about the procedure. So the way the techniques works is that you more or less take these two vector fields, x and y, and you start looking at flows along these vector fields, composed flows. And then we think of these t's. So these t's are how long you flow in a particular direction. So you flow along the x for t1, and then flow along the y for t2, and then flow back along x again. And if we compose enough of these flows together, then just by counting how many dimensions we have here, we see that, well, we could treat these t's like a coordinate system. Okay? So we imagine that we built as a highly degenerate coordinate system on Rn+1 by just composing these one-dimensional flows. The idea being that, well, if these two vector fields commuted with each other, then we wouldn't actually get all of Rn+1, but the fact of the matter is that in general they won't commute. And so you get a Kano-Karadeadores type situation, which says that even though we're only flowing in one of two directions at any given time, when you compose these flows, eventually you can reach any point in your Rn+1. And so it really does make a coordinate system, but it has a Jacobian determinant, which is going to be very often singular. Okay? And so what we know about this, so we know, for example, there's this trivial change in variables estimate that if I look at this set O, which is built from sort of a restricted weak type situation, if I choose to plug in a Jacobian determinant, then I just have a change in variable statement that says that this integral is bounded by the total measure of O, which happens to be what you get if you test the bilinear form on two characteristic points. Okay? So this is the integral that we have a trivial estimate from above, and all of the work is to estimate this integral from below in terms of something non-trivial. Okay? The only thing that we know about this set O is that if you look at sort of the flows in the x direction, for example, on the set O, we know that often the length of the set O in the x direction is bounded below by the total measure of O divided by the total measure of f. And the same thing, there's a similar statement that we can say that, well, if you look at the set O along the flows of the y vector field, then we can make an estimate from below as well. Okay? So we have this complicated set O, which is actually essentially a general set in Rn+1. We know a little bit of information about its sort of the lengths along a certain vector field and the lengths along a different vector field. And what we're going to do now is take this integral and try to peel off these t's one at a time. So sort of treat t2 up through t3 as fixed. Think of this as just a one-dimensional integral with t1 varying. And it's integrated against some function here that depends on t1. Of course, it all depends on the other t's, but those are frozen for the moment. And we know, roughly speaking, at least what the size of this set, what the size of this integral would be if there was no Jacobian. We know there would be at least as big as that. Okay. Okay. So, but the tricky part comes in that these t's, it's not necessarily true that one t is as good as any other t. And in particular, there is special significance to the situation when t1 is equal to 0. Okay. So because when t1 is equal to 0, this means you didn't flow on a vector field after all. Okay? So in each of these situations, if you set t1 equal to 0, if you look at the point where t1 is equal to 0, then you're well poised to do an induction argument, because you make a single one-dimensional integral estimate, and if you can use only information about what happens where t1 equals 0, then the remaining piece of information that you have has one fewer vector flows. Okay, and so you really literally can just sort of peel these t's off one at a time, but only if you restrict your attention to information about the Jacobian exactly at this t1 equals 0. Okay, and this is a serious. Just thinking about it for a second, this is a serious problem, because even for a polynomial, for example, if you know what a polynomial does at one particular point, that doesn't necessarily tell you anything about the integral that you're trying to do. For example, if you have because the fact of the matter is that any polynomial is large at some points, but that doesn't necessarily mean that the integral over the specific set that you're looking at will also be large. Like with the case of t squared. If you integrate t squared over a set which is very near the origin, for example, you're not allowed to estimate this integral in terms of values of t squared which are very far away from the origin. Okay? But at the same time, the point that we're looking at is pre-specified, and so we're not allowed to change points when this Jacobian function changes. We're sort of glued to this one specific point, and if we can't make an estimate of this integral in terms of what the Jacobian is doing at that specific point, then this whole procedure just fails. Okay. So this is why it's so critical that we sort of be able to push these simple one-dimensional integrals as far as they can go. Okay. So how does Tau and Wright handle this problem? Well, they introduce a new structure. Okay. They define what they call a central set of width W. So S, if S is such a thing, the main properties are that first of all it lives in some centered interval. It has a parameter W, which is non-negative, such that in actuality it lives in an interval of length W, and for all points in the set, W is saying that it lives in this interval from minus W to W up to constants, and the next feature is that S has the structure property that when you intersect it with an interval, you get some little gain. So you say that the intersection of S with any interval, the measure of that is less than S times some factor which relates to, well, what's the length of I in proportion to the width of the set S. Okay? It's a kind of a complicated condition. Informally, all that you need to know about central sets of width W is that on coarse scales they're very evenly spread over the whole interval that they're allowed to live on. Okay, and so it's only when you look at them at very short scales that they're allowed to be sort of clustered, but at larger scales they're very spread out. Okay, there's a very similar related idea introduced by Christ in 2006 that are called epsilon delta generic sets. So what they do from this point is that they show, so Tau and Wright prove a lemma, which is sort of really the crux of the whole matter. It shows that if you try to integrate a polynomial, for example, over one of these central sets, one of these sets with extra structure, then you can estimate the integral in terms of what the polynomial is doing at the origin. Okay, and the origin is in some sense a distinguished point for one of these sets because it's symmetric. Okay, so they say that so if you know what the polynomial is doing at this one specific point, namely if you know the value of the polynomial or any one of its derivatives is not small at this one specific point, then you're guaranteed that the integral of that polynomial over this structured set will also not be small. Okay. The downside is, of course, that this structure is very special, and the way that their argument works is then to take any generic Lebesgue measurable set in the real line and throw away enough pieces of it until they find a subset which has structure. Okay, and in the process, it gives them a loss of certain exponents, which prevent them from actually going all the way to the boundary of the type set, and proving all of the restricted weak type estimates that are actually true. Okay, so now the question really does become: so is it possible? To just use information about this function at one point and estimate an integral with respect to some measure? The answer is maybe, maybe not, because it's certainly true that there are some points which are there are some points for which an integral inequality of this form would just be false, right? If your point was very far away from the support of your measure, then it just doesn't work. And so the question is, well, are there any points for which it does work? And not only that, you need to know that it's not just sufficient for it to work at a point, but it turns out that for the idea of Tau and Wright, you needed to work for a large number of different points. Okay? You needed to work for a large number of different points, such that the collection of points for which it works should have almost the same size as your original set. Okay, so you need to say that, well, although it's not true for every single point, it should be true quite often. That all you need is information about one particular point, and you can then estimate an integral quantity from this one point information. Okay. Let me say for the purposes of this talk, we're going to speak only about polynomial functions. Okay. There you can talk about integrating functions which are more general than polynomials. But in particular, the sort of key thing that I want to say about polynomials is that polynomials have the property that if you differentiate them enough times, then look at the kth derivative, that the sup and the inf are comparable to one another. Okay, and that's the sort of main analytic criteria that we'll be using. Okay. So what's the what's the conclusion of all of this work? Well, the theorem is the following. So we suppose that we take mu, a probability measure that's supported on some closed set k that lives in an interval inside the real line. We'll suppose that f is a function whose nth derivative doesn't vanish. Okay, we're that's too strong. F is a function whose nth derivative does not change sign on I. So it's allowed to be negative or not positive, but it doesn't oscillate sign. Okay? Then the first theorem, which is sort of the less interesting of the two, but nevertheless related to the moment entropy inequality, is that if you take this function f and you integrate its modulus with respect to this probability measure, then it's bounded below by some constant times, well, the inf of the nth derivative on the interval, which is, like I say, it's sort of not great because we prefer suits to infs. But there's a constant here, this L to the power n. L is the inf of all coverings that consist of n intervals and cover at least 1 minus epsilon of the mass of mu. Okay, so this number L is roughly corresponds to the question. Well, if you're going to divide the measure mu into n pieces, what is the regular Euclidean size that you would have to accomplish to officially cover 1 minus epsilon of the mass? Okay, so this parameter L plays the role of an entropy, but the interesting thing is that it's defined not just it's defined not only in the case when this mu is given by integration against the probability of density, but it's defined for any probability measure. Okay, the idea being that as n gets larger and larger, you're allowed to break it up into more and more pieces. And this number L will only be small when the measure mu is very nearly supported on just n distinct points. Okay? Because that would be the situation in which you could, by taking n intervals of very short length, you could cover mu, which means that it's basically a collection of point masses. Okay? So that's the first result, but the sort of more useful one is one which follows from the first theorem, and it says the following: that if you take any probability measure supported on some closed set k, you pick your favorite n and your favorite epsilon, then there is a closed set E, which depends only on the measure. Okay? It's closed, it consists of at most n connected components, and so it's really just intervals and points. Okay? So it's a finite collection of intervals and points, such that, well, first of all, it has mu mass almost everything. Its mu mass is 1 minus epsilon or more. And for any function, for any, say, for example, polynomial of degree n, when you integrate the function f on with respect to this measure, it's bounded below by a constant times the sup on the set E. Okay? So what this means for us is that given any measure, there's actually a large collection of potential single points. The set E represents the collection of all single points, right? Because we could just replace the sup by its value at any one of the points in E. Okay. So in fact it says, so if we go back to the very first slide where there was this trivial estimate that said that you could always you could for a particular function f you could always throw away a large set and then find an estimate in terms of the sup. What this theorem is saying is that actually if you restrict your f's to be in the class of polynomials, then there is a single set which works for all polynomials. Okay, and this single set is E. Okay, and not only and it's not small; it's almost everything. Okay, and in particular, this is sort of an immediate corollary of this is that if you take a polynomial and you make this measure be a uniform measure on some set k, then we can estimate it in terms of f or any of its derivatives on some interval which is at least nearly 1/n of the original size of the set k. Okay, this is precisely the sort of estimate that you would need to push the tau right, work all the way to the end, and in particular using this you can, without much more trouble, you can go all the way and produce restricted weak type estimates on the boundary which were out of reach to tau right, just by changing this one-dimensional integral machinery. Okay, so how does it work? Well, the idea is that we're going to look at Lagrange interpolating polynomials. And after that, we'll multilinearize. But so we let V sub n be the van der Waals polynomial in n variables. We have a very nice we have a very nice formula which comes from studying the Lagrange interpolating polynomials, which says more or less that you can that if you sample the function f at n plus 1 distinct points and you multiply it by appropriate weights that are given by these van der Waals functions, then you get at the end something which is a weighted integral of the nth derivative of f. Okay. The way this formula comes literally from just taking you take the Lagrange interpolating polynomial that agrees with f at these t i's, you differentiate it the appropriate number of times, and show that their nth derivatives have to agree at some point. Okay, that's really all there is to this. And it turns out that this weight that you get actually has some other nice properties that are nice that can be useful, which is in particular this weight psi sub t is non-negative, has total integral 1. It's piecewise polynomial and compactly supported. Okay? And the breaks between the polynomials occur exactly at the t's. Okay? And this stuff is certainly, I just want to emphasize, there's nothing new about this at all. And in particular, you can find it recently in the paper of Backover that it's here in 2008. Okay. So once you have this formula, what we're going to do is multilinearize, which is again another idea which is very common in this whole literature, because these integrals are not only related to averaging operators, but you end up having to look at the same sort of thing when you talk about restriction inequalities and for the Fourier transform. And so it's all of these tools that have existed, but maybe never just been put together in this exact way. But the idea is that we take the integral for which we care about here, which is just the integral of the modulus of f, and we can multiply it by some integral of some multilinear integral of some van der Waals polynomial, and then using the formula from the previous page, it says that this quantity is less than or equal to this weighted sum of f, which is in turn can be expressed in terms of this integral of the nth derivative of f, right, times some other van der Waals. And we know, so we're in the case of theorem 1, we're assuming that this quantity has some sort of a minimum. Okay? And so at the end of the day, what we have successfully established is that we can estimate this integral from below in terms of simply a ratio of an integral of a van der Waals polynomial and an integral of a different van der Waals polynomial. Okay? The advantage of the multilinearization then is that all of the special features of f have dropped out, and we're now left with understanding some integrals of more or less explicit functions. Okay? So that's exactly what we do. We estimate this integral from below by this inf times the ratio of these van der Waals integrals. And there's the idea is that well, we know that these van der Waals polynomials vanish precisely when two or more of these t's coincide. And so you just take the measure mu. So roughly speaking, what you do is you take the measure mu and you try to chop it into pieces so that each piece contains a reasonable fraction of the total mass, and the pieces are well separated from one another. Okay? If you do that, then you can successfully avoid all of the places where these van der Waals polynomials are vanishing. And this is also where this covering by n intervals argument comes from, because these n intervals from theorem 1 are precisely the intervals that you would get by trying to take mu and separate it as well as you can into, say, n or n plus 1 different pieces. Okay. So this is roughly how theorem 1 works. But remember that the sort of disadvantage is that you've got an inf here of an nth derivative. This is sort of easily, so we made the assumption that the nth derivative of s, its inf was comparable to its sup. So for sort of trivial reasons, you can replace it with a sup, which is better than what we had. But we would really like to remove this derivative altogether and for the second theorem, just estimate it in terms of the value of f and not necessarily a derivative. Okay. So the way that we accomplish that is we now take this this estimate that we have, which is sort of trivially, we replace this inf with a sup, and in the process we came up with n different intervals, and we restrict the measure mu to each of these intervals one by one. We do the same decomposition again. We reduce n. So we have sort of an induction argument we're doing reverse induction from n down to 0 derivatives. And we just apply the same argument over and over again. At the end of the day, we get a collection of n factorial integrals, but this is not a really serious problem. You can play around with it and show that you can join a bunch of them together. And at the bottom level, we get that the integral of this quantity is bounded below by some constant times the soup of the modulus of f on all of these n factorial intervals. Okay. The only catch is that, well, certainly in order to actually perform this induction argument, we would need to know that on one of these intervals, the n minus first derivative has the property that its soup is comparable to its if, which is not always true, right? Because I mean, it's certainly true for the highest order derivative of a polynomial, but if it vanishes on that interval, then it's certainly not true. Okay, so it's not immediate that you can actually run induction. But the interesting feature is that it turns out that if you're in the situation where you don't have comparability, then even if you could run induction, you wouldn't end up getting an estimate which is any better than the one that you already had. Okay, so the bottom line is that sort of because of this sort of interesting dichotomy, that either the j minus first derivative is comparable to itself, or it's smaller than the jth derivative in some sense. So you run the induction argument, and if the induction argument fails, then you get to write down the inequality that you want anyway for free, because it's not as good as what you have already proved. Okay, so you just induct when you can, and when you don't have to anyway. Okay, so then the question becomes, what happens in higher dimensions? And certainly in higher dimensions, there's an immediate problem which comes from the fact that even in 2 dimensions, you can't make an estimate like this. So this was the special case of the moment-entropy inequality, for example. You can't make an estimate like this for any function f whose sublevel sets have infinite measure, for example. So if the sublevel sets are allowed to extend out, then just something like this can never be true. Okay. So in one dimension, we really are relying on the fact, more or less, that that the structure of the zero set of this f is really discrete. Okay. So you can try to play games by restricting your e to lie in the unit square, but even then, really all you're doing is the same one-dimensional estimate that we've just done plus Fellini, and you're not really getting the full strength of what should really be true. Okay, and so it turns out that what the thing to do is instead of looking at a single function, the right thing to do is look at relationships between various functions. And in particular, an example of such an integral you might want to look at is the following. So you have, instead of looking at a single set E, you look at integrals on E cross itself. And you now ask, okay, well, how often in the pair E cross E do we have, for example, a function like this, determinant function? So when can we say that this thing is bounded below by some constant times a power of the measure of E? This type of integral very much appears in the literature all over the place. It's not particularly well studied, but it turns out that this does appear to be the right generalization of the one-dimensional situation, in the sense that that it has the same property that you can prove results in this direction. Let me skip this one. So you can prove results in this direction for multilinear objects like this that are really valid for arbitrary probability measures and beyond. Okay, so the fact of the matter is, so the theorem is the following. So take any measure mu, which is finite or sigma finite, and suppose that it has the property that when you test mu on boxes, so these are just regular rectangular boxes, but they might be rotated. If the mu measure of a box is less than some power of the Euclidean size of that box, then this is a condition which has shown up in one dimension, for example, in the context of the restriction, Fourier restriction problem, and Backward-Willen here. It turns out that regardless of the dimensionality of mu or anything like that, that this condition here, this inequality between the mu measure of B and the Euclidean measure of B, is necessary and sufficient for a multilinear object of the following form to be bounded on a product of LP mu spaces. Okay, so this is really what I think the right analog is and the right sort of place to begin. And so I'll leave it there.
Right. I know it's a silly question, but I'll ask it anyway. Is there any hope of classifying gamma, at least for a reasonable consistent bits?
Yeah, so you can in fact, there's a very, I didn't write it down, but there's more or less an explicit relationship between what this gamma is and what this exponent theta is.
That's what I'm looking at.
Yeah.
Can I?
Sure, yeah.
Okay. All right.
Any other questions?